Okay. Yes. Number 2. If 1 megajoule of heat is transferred to 10 kilograms of water initially at 15 degrees, what is the final temperature? Okay, here we go. Here's number 2. So that is heat. So that's Q. Q is 1 megajoule, and a mega is a million of something. So this is going to be 1 followed by 1, 2, 3, 4, 5, 6 zeros. 1 million joules is being transferred to a mass of 10 kilograms of water. 10 kilograms is 10 liters. That's 2.5 milk jugs. Just putting in perspective of water. The water is at 15 degrees. That's your initial temperature, 15 degrees Celsius. And we want to know what the final temperature is going to be. So we're going to use Q equals MC delta T. So 1 million is going to equal 10. The C value of water is 4,200. And delta T, the change in temperature, is your final temperature, T final, which is what we're looking for, minus your initial temperature, 15. So to make our life a little bit easier, this is going to become 1 million. We're just going to multiply these two together, just adds a 0, to become 42,000 T final minus 15. And now we go ahead and just, use some algebra to solve this thing. We're going to solve it by dividing both sides by 42,000. That's going to cancel that. So we're going to get 1 million, 1, 2, 3, 4, 5, 6 zeros, divided by 4, 2, 1, 2, 3 zeros. And we're going to get 23.81 is going to be equal to T final minus 15. We're going to add 15 to both sides. And we're going to get, boom, you add 1 million joules to 6.5, no. What did I say before? 10 liters, 2.5 milk jugs. You add 1 million joules to 2.5 milk jugs. And then the water temperature is going to become 38.81 degrees Celsius. A bath. That's a lot of energy for not a lot of payout. It takes a remarkable amount of energy to heat up water. EREM, does that make sense? Okay, then, if there are no further questions, going once, twice, thrice sold, let's talk about how we do this. How do you give all that water 1 million joules of energy? We're looking at thermal energy from power sources. This will be our last lesson, all of Physics 11. We know that you can change the temperature of an object according to the equation Q equals mc delta T, where Q is the amount of energy, delta T is the change in temp, M is the mass, and C is the specific heat capacity of whatever material you have decided to heat up. And there's some interesting implications with some of this stuff that should you go off into chemistry, you will see. Because, I'll just casually glance over here for a second. If you go back and look at the specific heat capacity table, water has a huge specific heat capacity. Alcohol, or methyl alcohol specifically, is almost half the specific heat capacity of water. And so if you have a mixture of these things, heating them, they'll heat at different rates. The mixture of alcohol and water will heat at different rates, and they'll boil at different points. So in chemistry, one of the things that you'll look at is how do you separate out different substances. One of the separation techniques is called distillation. You can remove the water from something because it boils at different temperatures and absorbs heat differently than other objects do. This handy dandy little equation branches out over to chemistry as well. But here, let's keep going with it. Q equals mc delta T. To do this, we have to provide energy to the object. We have to get it there somehow. One way to provide the energy is through an electrical element, like a kettle or a hot plate. Another way to do it is through a microwave. Some device is going to convert electrical energy in the wall, or a battery, usually the wall because the batteries will just wipe out, into usable thermal energy. Recall that 1 watt, the units we have for power, is equivalent to 1 joule per second. So every second a 1 watt power supply is running, 1 joule per second is being transformed or transferred to another object. So if you take a microwave, a typical microwave might be 1200 watts. I have a microwave over here. Let's take a gander. Ooh, here we go. Nope. Stickers on the back. I'm not turning that thing around. Don't know what the wattage of my microwave is, and that's okay. A typical microwave might be 1200 watts. Who'd you like? You may. Irem. 1200 watt microwave. What this means is if 1 watt is 1 joule per second, that means the microwave is equivalent 1200 joules of energy every second to whatever is inside it. And so now you've got this idea where we can, based on the wattage rating of these objects, we can figure out how much energy is being produced by the object. If you turn on the microwave for 1 second, how much energy have you given your food? Well, it's 1200 joules. It's 1200 joules per second. For 2 seconds, how much energy have you given your food? 1200 joules per second times 2 seconds, 2400. If you leave it on for 30 seconds, how much energy have you given your food? 36,000 joules. So, we get an equivalency here that will give us how much energy has been transmitted to whatever object we want to heat up. Energy is equal to the power rating times the time that you run that power rating for. But what if you don't microwave on high? What if your element is not totally covered? Or what if the pot you're using is too big for the element? What if the element is only allowed to use a little bit of the bottom of the pot because you've decided to put your gigantic pot on the small element? Well, what that means is you've got a percentage that's missing. If you don't microwave on high, and you decide you wanted to use one of the lower power levels, what these power levels mean is, generally there's only 10 levels. Every level represents 10% of the available power. If you put the thing on power level 8, what this means is you're using 80% of the total power. Nope. Which is part of the conversation. I don't know if she heard me. She needs to have. So using 80% of the total power. If you microwave on power level 8, what is the power output going to be of the 1200 watt microwave? Well, you're taking the 1200 watt microwave and you're only allowing it to produce 80%, or 0.8 of the available power. What is 80% of 1200? Or what is 8 times 12? 80% of 1200 is 960 watts. What that means is, if you recall, it's going to be 960 joules every second. We can put these formulas together. We can take energy equals power times time, and Q equals mc delta T, and we can combine them, where this guy, I'm going to use a different color, this guy is a form of energy, this guy is a form of energy, and we're going to put this expression right here. We're going to get power times time is going to equal the mass times the specific heat capacity times the change in temperature. We also had another expression. Power is equal to work divided by time. So if we really wanted to, we could change this expression. We could say that the work divided by the time times the time equals mc delta T. Those are going to cancel, and we'll say how much work did we do is going to equal the change in temperature for the thing. We had a bunch of different expressions for this too. We had work is equal to a force times a distance. You're going to get all sorts of interesting here. You can start to calculate now how friction is going to heat up your objects. Because if work is equal to a force times a distance, we can say that a force times a distance is going to equal mc delta T. And we can start talking about how friction heats objects. We're not going to, but we could, and that would be interesting. This guy here is the one that we're going to use most today. When you're ready, flip the page. Okay, so we have a 600 watt kettle. It's used for 3 minutes. If you were heating 1.5 kilograms of water, and recall 1.5 kilograms is 1.5 liters, what is the change in temperature? Well, that's a power rating. The power is 600 watts. The time we're using this for is 3 minutes. The mass of the water that we're heating is 1.5 kilograms. And we want to know what the change in temperature is. And this thing is water. Water has a C value of 4,200. What we can do is we can take these things, we can slap them together and say, okay, well, power times time equals mc delta T. The power is 600. What do I have to do with this time value? Convert it to seconds. To take minutes, put it into seconds, we do what? Times by 60. It's going to give us 180 seconds. So we're going to get 600 times 180 is going to equal the mass of the water, 1.5 times 4,200. And we're not looking for a final temperature or an initial temperature. We just want to know what the change is. So this is relatively easy to solve. It'll be 600 times 180 divided by 1.5 times 4,200. Solve this thing, delta T is going to be roughly 17 degrees, 17.1. So 3 minutes with the kettle is only going to change the temperature of that water by 17 degrees. What if instead of the kettle, we're going to use the stove, hot plate? The hot plate has a power of 800 watts, so it's a stronger hot plate, but our pot doesn't cover the whole surface. The pot only covers about 60% of the surface. So we're using a pot that is smaller than the total area of the element. So we're not getting all 800 watts. We're getting 60% of that. How much power is actually being transferred? Well, the power available is the total wattage times the percentage as a decimal that's actually being used. 8 times 6 is 48. So 800 times 0.6 is going to be 480 watts. If we heat the same amount of water for the same amount of time, what's the change in temperature going to be? Well, it's still PT equals MC delta T. The power times the time is equal to the mass times the specific heat capacity times the change in temperature. P is 480. T is still 180. The mass is still 1.5. The C value is still 4,200. What is the change in temperature going to be if you use 60% of this hot plate? That, Colden? 13.7 degrees. Even though the hot plate was rated to be better, if you don't use it effectively, it's going to give you a worse outcome. That is one way to heat an object. You put it on an element, or you pour it around the element. That's how a kettle works, the electric kettles. The element's inside there, heating up the water surrounding it. But another way, the old school way, to warm these things up or to cool these things down is through conduction. And I have seen this in person before, and it is a mess. Another method of heating an object is to add something hot to something cold, or vice versa. And allowing conduction to transfer the heat. Imagine, if you will, we want to heat up a pot of water. So here's, or in this case it says cool glass of water, but glass is a terrifying object to use here. If you heat it up too fast, you'll shatter it. But you have your glass of water. There's the glass. Let's fill it full of water. The thing is cool. Perhaps you've seen these videos on social media where they take the glass of liquid or the container of liquid that's cold, and you decide to add a boiling hot piece of metal to it. You take this thing and you insert it. What's going to happen as soon as that hot object enters the water? I mean, it's going to depend on the temperature of the water, but it certainly could boil. Generally, if the metal is glowing like that, it's going to be ridiculously hot. But in the interim, like, think about where the energy is and what's the energy going to do. What's going to happen to all of the thermal energy in that hot object? Sorry? It's going to leave the object and go where? Into the water. Thermal energy is going to flow from an area of high thermal energy to low thermal energy until when? Until they're equal. Until they reach same temperature. And we say that they have reached thermal equilibrium at this point. And at that point, the energy is going to stop flowing. Because one doesn't need to give up and the other one doesn't have any space to take. So when you're ready, flip the page. Let's look at the math behind this kind of thing. When you're mixing two objects together, we can look at it this way. We can say that when you have two objects, you take one hot object, you put it into another, or a cold object into a hot thing. Do this at home all the time. You have the boiling hot soup. You take the ice cube because you don't want your child to burn off their face. You put the ice cube into the soup, and you see what's going to, like, you see the thing melt. The soup gets cooler. But I mean, we could actually do the math to determine the temperature that the soup will reach at the end. You could. No one's ever thought about doing that, perhaps, but you could. There's no reason why it couldn't happen. And how it works is this. We say that the thermal energy lost by the hot object plus the thermal energy gained by the cold object has to be 0, because all of the energy from the one object is going into the other object. So this guy right here is the energy out of the hot object, and this is the energy into cold object. And if you add those together, they should be 0. If it's not 0, it means you've lost energy somewhere, which in the real world is likely. So having it equal 0 means we're assuming no energy is lost to the surroundings. We know that's not true, but for the sake of what we're going to do now, let's pretend. And this is what it's going to look like. A typical question for this could be, you have 0.06 kilograms of aluminum. You heated it to 90 degrees. That is the current temperature of the aluminum. You added it to 0.09 kilograms of water. So that's 90 milliliters of water. That is 2 tablespoons of water. Just to give you, not TSP, tablespoons. 0.09 kilograms of water is 2 tablespoons of water. What will be the final temperature of the two after thermal equilibrium has been reached? Let's figure it out. Well, we know that Q for the hot object, in this case the aluminum, plus the Q for the water has to equal 0. Well, we know Q is equal to MC delta T, so we're going to have the mass of the aluminum times the specific heat capacity of the aluminum times the change in temperature of the aluminum plus the mass of the water, specific heat capacity of the water, change in temperature of the water. It's going to equal 0. So we can start filling all this stuff in. The mass of the aluminum is 0.06 kilograms. The specific heat capacity of the aluminum is 920. You can find that on your formula sheet. The change in temperature of the aluminum, remember, delta T is equal to the temperature final minus the temperature initially. We don't know what the final temperature of the aluminum is. That's what we're trying to find. So T final minus, what is the initial temperature of the aluminum? 90. So we've got MC, change in temperature, plus the mass of the water, 0.09, the specific heat capacity of the water, 4,200, times T final. We don't know what that's going to be, but we do know that the temperature final of the water and the temperature final of the aluminum have to be the same. They will meet somewhere in the middle. And the initial temperature of the water is 20 degrees. We know the sum of this is going to equal 0. And now this is the algebraic expression we're going to solve. To make your life a little bit easier, you might have algebraic techniques that you prefer. I'm going to show you how I would solve this thing just to make your life a little bit easier. If you don't have your own techniques, I would simplify wherever I can. Multiply these two things together, multiply these two things together so you get a simpler expression. We're going to get 55.2. That's what you get when you multiply these two values together. T final minus 90 in brackets, plus this is 378. T final minus 20 equals 0. And now, because we've got the T final, the thing we're looking for, shows up in multiple places, the next step is to distribute the thing that you're multiplying each bracket by into the set of brackets. Distribute this guy here and here, distribute this guy here and here. You're going to get that 55.2 T final minus 4,968, 55.2 times 90, plus 378 T final minus 7,560, the 378 times 20, is going to equal 0. I thought I left I need one more line. Thought I left myself enough space. These two are just numbers. They're both negative. We're going to add them over to the other side. And we're going to combine these two terms. They both have the T final thing that we're looking for in them. When we do that, what we're going to get is that 55.2 plus 378 is going to be 433.2 T final, and that's going to equal, when we add these things both over to the other side, we're going to get 12,528. The last step. Divide both sides by 433.2, and you're going to find that your final temperature is a balmy 28.9 degrees Celsius. There's a lot there. Questions about what I've done? Give you a second to absorb it emotionally before I move on. Questions, comments, concerns about what I've done? Okay, I've got one more question for you, and that'll be it for me for Physics 11. Another application of this is this kind of question. A new metal is discovered and we want to determine its specific heat capacity. Or if we actually had time to do this last lab, another way to say this is you don't have a new metal, you have an existing metal. You don't know what it is, you want to find it. What is, I hand you a metal, I say, okay, what is this metal? There's a bunch of different ways that you could figure out what that metal is. You could find its density and compare it to density of known metals. You could find its conductivity and measure it against conductivity of known metals. Or you could find its specific heat capacity and compare that to known metals. And here's how you do it. If you've discovered a new metal, we want to determine its specific heat capacity, or I hand you an unknown metal and you want to determine its specific heat capacity, Rena, wake up. In order to do this, what we're going to do is we're going to heat it, 100 grams of that metal, to 100 degrees Celsius. Just so we're really clear, how do we do that? How do you heat 100 grams of metal and guarantee that that metal is at 100 degrees Celsius? Is there anything that you know that exists at 100 degrees Celsius? Boiling water. Boiling water will, and this is, perhaps you don't know this about boiling water. Colden, I don't know what you're doing, but stop doing it. And Dwayne, William. Water, as you bring water to a boil, it will remain at 100 degrees Celsius until the water is gone. It doesn't exceed 100 degrees. It will stay there until all the water has boiled away. The only part of the water that's above 100 degrees Celsius is the steam rising from the top of the pot. The liquid stays at 100 degrees until it's gone. So all you do is you boil a pot of water, continue it boiling, and you add your metal to it, and you wait until you can be reasonably sure that that piece of metal is at the same temperature the water is. You might wait 10 minutes. You want to be really safe. You wait 20 minutes. It's going to reach 100 degrees Celsius. And then what we're going to do is we're going to take it out really quickly, and we're going to drop it into 1.1 kilograms of water that we know is at room temperature, and we're going to see where the temperature rests. We know the mass of both objects. We know the initial temperature of the metal. We know the initial temperature of the water. We measure the final temperature of the mixture rests down to 28 degrees Celsius. We can find the specific heat capacity of the metal. All mixing starts here. Temperature of the metal, or the energy of the metal, plus the thermal energy of the water is going to equal 0. Because all of the thermal energy from one is going to be given to the other. So we have the mass of the metal. We have the specific heat capacity of the unknown metal. The change in temperature of the metal, plus the mass of the water, the specific heat capacity of the water, plus the change in temperature of the water equals 0. And we can fill all this in. The mass is 100 grams. We want that in kilograms. So 0.1 kilograms times the specific heat capacity of the metal. That's what we're looking for. Times the change in temperature. We have that. We know the metal started at 100 degrees, and the metal and the water met at 28 degrees. So this is just going to be 100. Final temperature, 28, my bad, minus initial temperature, 100, plus the mass of the water we know is 1.1. The specific heat capacity of water is 4,200. The change in temperature of the water, its final temperature is 28, minus its initial temperature of 20. It's going to equal 0. For the sake of this, I'm going to go ahead and I'm going to punch this into my calculator for you. This whole thing, 1.1 times 4,200 times 8, 28 minus 20 is 8. This whole piece here should equal 36,960. Is this piece right here. This thing is negative 72. And so what we're going to get here is that the specific heat capacity of the metal times negative 72 times 0.1 is going to be negative 7.2 plus 36,960 equals 0. That is an expression that you should definitely be able to solve. We're going to subtract this guy over. We're going to divide by that. So we're going to get to the specific heat capacity of the metal. It's going to equal negative 36,960 divided by negative 7.2. And you should find that the specific heat capacity of that metal, whatever it is a ridiculous 5,133.3 repeating joules per kilogram degrees Celsius, which I'll have you know is not possible for a metal. But there it is. That's the value. Questions, comments, concerns about what I've done? Yes, sir. Metals are way better conductors than that. That's part of the definition of being a metal, is having good conductivity, and a value like this is horrendous conductivity. This is reasonable conductivity, though, Oh, yeah? Yes. Just so for those of you who might be interested, the specific heat capacity of the ceramic tiles on spacecraft equals, for those of you who might be interested, 6. I'll make sure I get this number right. 0.628. Oh. You know what? Sorry, my bad. I misread what I wrote. Forget what I said. Forget what I was about to say. That's not possible for metal, and we'll leave it there. My apologies. Okay, so this is it. This is the last little piece of Physics 11 from me. I would like you to play with these two methods of heating things up. There are 9 questions here. I want you to do all of them. Some of them are going to be heating things using power sources. Some of them are going to be heating things via mixture. Use the appropriate style of heating equation to determine whatever piece of information they're looking for. On your mark, get set, giver, you have about 22 minutes left in the block. Use this time. Let me know how I can help.